Yay.
So hi students. Thanks for joining us for our pathway presentation today. The first you'll hear from Dr. Saklis, who's joined us from the controls area. He's also the undergraduate program chair for electrical engineering at ASU, and we're glad you could join us. So thanks, Dr. Saklis, for being here. Students, if you have questions and you want to put them into the chat, that might be the best place to do it, and then we can get to those at the end of the presentation. So thanks. We're ready to go when you are.
Well, good morning, everybody, and I'm going to give you a brief introduction and controls and discuss a little bit of the program. So here we start. I think you're seeing my screen. Are you seeing also the
No, it's just the slides. It looks great.
just the slides? Okay, good.
Yes.
So we're looking at big changes in controls relative to what has been developed over the past century or so, where controls has been really active. It's a fairly old area. And what is different now is the abilities that we get based on the recent computer developments, the computing technology, and the sensors that we have for different processes. And we can implement new technologies and doing amazing things. Intelligence is part of controls. One of the definitions of intelligence has to do with feedback. And the intelligence systems are here, and they do require proper design of feedback. Part of the excitement and the benefits of feedback is that we can get performance, better performance than without it. But there is a trade-off in terms of making sure that the system stays stable. Feedback can destabilize the system. So a proper design is typically required, and the proper implementation, understanding the trade-offs, and so on. Okay, so we're going to talk about the main issues, just get a brief introduction of what kind of problems we're looking at in the controls area, the typical applications, and of course, what's of interest here is the courses that are associated with the controls area within the general systems area. This is a very typical feedback loop. It's an abstraction. Feedback is inherently stated as an abstract problem. And the reason is that it gives us the ability to use the same type of formulation for different applications and adapt the tools, the techniques, the computational tools that we have to each particular problem, which may be coming as aerospace. You see pictures in this slide. So aerospace is a big area of applications. Manufacturing is another one, in particular semiconductor manufacturing, which is a big area in the valley. Even when we look at reactors, I believe this is a molecular beam epitaxy reactor, or even small drones. You see the ornithopter with the scent. That's an exciting application. So we have feedback loops, which in that abstract sense, they have essentially a couple of components. One of them is the plant that is controlled. The other one is the controller that we design. And the interesting part here comes from the signals that enter this loop. They can be disturbances that come from the outside. They can be desired commands we try to follow, and sensor noise. So the controller is trying to balance all these disturbances. It tries to control the system, track a desired output, and reject or at least attenuate the effects of disturbances, and that in the presence of model uncertainty. All these things have to be formulated in a precise way so that we're able to translate the problem into math and generate solutions. Another problem that you can use to relate to the control statement is where we have a vehicle and we try to achieve cruise control. So we have a desired speed as a reference command. There is an actual speed that we measure, and we manipulate the fuel flow to the engine by changing the position of the accelerator, and that's what the controller is doing. And again, you see several pictures from aerospace to robotics, which have provided some of the more, let's say, iconic applications of controls. The first big applications of control systems were in, at least in the last century, in the more recent years, were in amplifiers, telephony, and communications, and aerospace. Flying airplanes, especially high-performance fighter airplanes. And more recently, we look at a lot more applications in robotic mechanisms and so on. So we'll talk a little bit more about different areas of applications. I did mention about the main issues in the control problem. We have models that can be quite complicated. They may contain nonlinear dynamics. They may be non-invertible as systems. So it's not easy, in other words, to infer what the control should be given the output. And there is always uncertainty in the models. And that's the primary objective of the controls, being able to achieve specifications, achieve certain type of performance, despite uncertainties in the system models. So we need to quantify what we know about the system and how much we can do. And that's perhaps the more exciting part of the controls, that it's able to quantify what can be done, even if information is not perfect. On the implementation of controllers, things that do come up recently, because we are doing a lot more computer-based controllers and computer-controlled systems, we are interested in specifying precisely what kind of sampling rates we can use, how we can actuate, and how we can measure, dealing with issues with analog to digital and digital to analog conversions, and what kind of measurement noise we have. Now, the type of design is based on modeling the system, performing simulations to evaluate what can be done, and also validate the designs that we do. The fundamental question there is to determine realistic specifications, which is not always obvious and it's not easy. It's easier in homework problems when the homework problem comes in the form design a system to achieve uh, objective number one, let's say phase margin 50 degrees. So some specific numbers to predefined quantities. But it's a different story when one is looking at the actual system and there is nobody to provide these specifications. So the specifications need to be determined according to what can be done, what's realistic to be done. The design of the control system goes through certain types of procedures. It's usually based on an optimization process. In some cases, in let's say simpler cases, where an exact performance is not required, there are simpler rules, simpler procedures to design controllers, down to the point of using back of the envelope calculations, to more sophisticated and more elaborate techniques where we use high-level optimizations, scheduling several controllers together to cover nonlinear operating regions and so on. The implementation has a lot of excitement nowadays because we have a lot more capabilities in terms of microcontrollers, DSPs. We can do rapid prototyping with fairly cheap hardware. For example, Arduino class processors, which can be used to control a lot of processes, at least with simple controllers. And they do enjoy a lot of applications in robotics, from the let's say hobbyist level to certain class of industrial level applications. And of course, we are interdisciplinary. Control by itself is not tied to a particular area, but it can serve many areas. And that's where it's interesting to look at multidisciplinary applications, and also for the control engineers to have background from diverse areas, so that they can understand the problems in that area. Let's say an aerospace engineer will not necessarily define what the control problem will be. They may be able to describe what they want to be done, but it's the wish list. But it's the job of the control engineer to understand it and translate it to a solvable mathematical problem. I'm listing up different areas of application here. We talked a little bit about the aerospace and the manufacturing. Biological applications are also of big interest in these days, both in terms of prosthetics, trying to use prosthetic devices for people with disabilities, or even dealing with epidemics and cardiovascular control systems and so on, pacemakers, in other words. Capital investment is a potential application because there is some kind of a feedback process. We're measuring quantities and we try to maximize some performance in terms of return on investment. Of course, what's very difficult there is to establish a model, but it has been known to produce some results. defense is one of the big sectors of control applications, missiles and guidance problems, uh, and so on. And I've talked about some of the rest. Space exploration is always one of big interest. And one thing which is particularly interesting there is that the device, the system that is controlled is not necessarily close to anybody who can do maintenance. And I'm sure you've seen the recent news from Mars, the helicopter that they had there operated for a very long time, and eventually, of course, there will be failures in those missions. But what's interesting in terms of controlling that device is that the delay in terms of communication is so long that the only thing that the humans can do from Earth is send some general commands or what is expected, and from that point on, the helicopter or the robotic mechanism should be able to do tasks autonomously or at least semi-autonomously, receiving commands infrequently. Okay, now in the more tangible type of information, what kind of courses are associated with the area? We start with 202 as a prerequisite for pretty much everything. It's basic circuits, but it also introduces dynamic behavior of systems, in particular circuits in this case, but that behavior can be extended to other systems. So second order oscillatory system with some damping ratio, it can be a circuit, but it can also be a mechanical device, a suspension system for a car, and so on. Of course, the math background involves differential equations and transforms, and in particular, linear algebra is important in controls, exactly because at this point, most of the computations are heavy on linear algebra. We use a lot of results from linear algebra to perform optimizations and computations. The first courses in signals and systems, 203 and 304, we look at the development of background, and in particular, 304 has some introduction to control systems and digital control. Then at the senior level, 480 and 481. 480 is classical control, dealing with specifications, how we design controllers in a classical sense. Classical sense means frequency domain techniques and using simple calculations of phase margin, gain margin, so some of these traditional concepts. 481 has some of these elements, but is focused on discrete time control and embedded controllers. So in other words, control systems that can be reasonably small and contained so that they can be put on devices or on systems for the implementation. At the graduate level, the linear systems is probably the fundamental course to take, which is a prerequisite for pretty much everything else. right now, we're also trying to introduce adaptive control uh, as uh, a course which is of interest in robotic applications. So in the RAS program, uh, these two will, linear and adaptive, will follow each other as fall and spring semesters. And then optimal control and neural nets are the other two that keep running most of the time. Nonlinear system transforms, random signal theory, filtering, those are also courses which are in the graduate program. Applied optimization and numerical analysis is always highly recommended, at least from my perspective, very useful courses. And system identification is a related course. We do some in adaptive control in the latest version. So that's the general outlook of the controls program. You see here the area. There are some connections with quantum computing, which are starting to materialize. Christian Arends is in that area. And our topics are the topics of, let's say, focus or more interest is in the modeling, in the controller design, adaptive systems, neural networks, fault detections, and real-time applications. Okay, and then you'll see the slides. You can get access to the slides later on. You see potential job opportunities, and there are connections with several of these types of companies. Okay, and I'm going to leave all that in the interest of discussing more questions. You'll see different applications and get an idea of, let's say, areas of specializations that you may have. And that's more in the sense of trying to combine control systems with other application domains to become more marketable, for one thing, and achieve interesting results. Okay, so I'll stop here. I'll leave you with the information in the slides and links if you want to get deeper into the subjects. And of course, you can always email me, ask questions if you have anything more. Okay.
Thanks, Dr. Saklis. Students, we might have a couple of minutes for questions if you have it about controls area specifically. And we usually get a couple of questions along the way. If not, just keep in mind that we'll put the link to the this session, and we'll also have the link to the, we should add the link to the faculty by research area. If you're curious about controls learning more, we have multiple faculty who work in this area besides Dr. Saklis too. So far, we have a quiet group, so I don't have any questions for you at the moment, which means you were very thorough.
Okay. I'm not going to object to that.
Yeah. Well, thanks. Yeah, thanks for the.
I can give 5 extra minutes to Martin.
Oh, there we go. We have one question. I knew we'd get one if I.
Okay.
Oh, what do you think from Yasina? She's asking is, what would you like to see improve in this particular area, or what courses might we need, or what improvements can be made to the controls area?
I'm not sure what's the meaning. The most room of improvement in terms of applications,
I
or
suppose, or the actual curriculum area. Or, she said yes to applications. Yeah.
Okay. Um, I'm not sure if there is a single answer to that. Things that are popular right now, they are in robotics. That's where we see, let's say, a lot of the graduates going into when I say robotics, I also mean automotive, the uh, vehicles, automatic driving, and these types of applications. Uh, but there is, yes, fiber optics. I don't know if there is a control problem which is associated directly applying onto fiber optics or using fiber optics
Communication,
as a
right?
medium of communication. That's another possibility. But as a um, okay, I didn't finish with the areas. Uh, the manufacturing is a big area that receives interest. Aerospace always has a big chunk of controls people, uh, and I did mention the prosthetics and the bio applications. Uh, so in all of these things, you can find uh, different applications that can make the difference in, let's say, uh, getting a better product. So the innovation, and the power of innovation uh, can be quite big. Uh, the undergrad research.
We'll get a link to that in there's a formal area that you can look through a whole bunch of stuff. So we'll put that on there. So besides working with individual faculty who might have projects, we have some other links that we can share about undergraduate research stuff. But Costas, or maybe Dr. Reislein too, I mean, have you worked with undergraduates on research in the past, I imagine?
Yeah, so the last one, yes. There are FPGA controllers. Well, uh, as far as I know, mostly power area. I'm trying to stay with microcontrollers, Arduino class. Um, and there are a lot of different ones in that class, and some of them are extremely powerful. So yes, I typically give a few senior design projects on that.
Well, thanks. I think we might transition some of this stuff already. Angel says thank you for that, but we will have a seminar on capstone projects coming up soon. So make sure to join that if you want to learn about more ideas and talk to one of the capstone faculty who will present. But yeah, thank you, Dr. Saklis. I think we should. It's just about time to move on to the signals
All right,
area.
thank you
If
all.
there's others, but yeah, thanks for being here. We appreciate it. And our next presenter, as we get set up for that, is Dr. Professor Martin Reislein. He's also our graduate program chair for the computer engineering program, and he's a faculty member with a communication and signals background. And Dr. Reislein's great. So thank you for being here, Dr. Reislein, and go ahead and
Sure,
start when you're ready.
Let's set up the presentation. Do you see it full screen now?
Yep, looks good.
Perfect. Okay. Good. Yeah. So, morning. Welcome to the signal processing communications presentation. I'm not the group leader per se, as Professor Spanias, or rather Professor Lay currently is leading the group, and I'm presenting on their behalf. I'm communications, or rather networking, computer networking, but I'm part of the signal processing communications group. So signal processing in itself is a bit marginal, it's a marginal area to me, myself personally, but I'm in this group. So I have big picture overview here as well. So let's start from signal processing, then we come to communications later. So if you've taken a signal course already, you know there's some physical information that's being collected. And there's a whole area about sensing, sensor devices that is more physically oriented, that deals with collecting this information. Signal processing works on manipulating, making sense of these signals. An example here shows an ECG signals. A lot of the signals nowadays are medical signals, or as Professor Costas mentioned earlier, medical devices, prosthetics, robotics, all these have signals that are being processed in a signal processing system. And then we provide some output that's infers controlling typically, but from a signal processing perspective, controlling the device. Yeah. So signals processing and controls are related, but they have distinct flavors. Yeah. Here's some examples now to go further into signal processing. So multimedia plays a big role. So you see voice here. There's video. Again, on the slide, you also see the medical relationships. Image processing also with medical imaging plays a big role, and then DNA and sequences are also. These are all types of signals that are being processed by signal processing algorithms. Pivoting more towards communications, you may be using a 4G, fourth generation phone. Right now, we are moving towards the fifth generation, 5G, and the 6G is on the horizon. We are by 5G and 6G are moving more towards machine type communication. The consumer is less to benefit, but it's more about controlling machines, industrial manufacturing, low latency communications, again, to support these controls types of applications. On the right side, you see here then the satellite or other boundaries that are currently being explored, space, underwater. All these pose particular challenges for communications and networking, and all these are being addressed in the signal processing communications group and courses. Any questions so far about these application areas? Please feel free to interrupt if you have a burning question. Then moving on slightly in the more networking, smart grid is a combination of the power grid and communications grid. You may have heard about smart meters that have been installed that allow for demand response control of power consumption. That requires a very tight internetworking of these power consumers, producers, and the communication network infrastructure to pull off this control. Similarly, wind and solar, all the sustainable energy consumption and production and consumption requires tight control that is being facilitated by communication networks. So communication networks are the underlying glue that holds all these distributed systems together. So it's a very, very important technology. At ASU, we have a special type of signal processing also. That's the signal processing arts and media, AME, that fuses elements of performing arts from the Herberger College of Fine Arts with signal processing. This is a small part of the signal processing program, which is very interesting if you're interested in fine arts. Next, here we have a list of our faculty in the signal processing communications. You see this list is a bit longer than for controls. The signal processing communications group at ASU is fairly large. It's one of the largest in our school.
Control circuits and different course pathways for my year 3 and 4.
Yeah, we'll get the courses. Very good point. We'll get the courses next. Okay, so these are the folks teaching the courses, and then next we get to the courses. So good point. Yeah.
Some of the courses that I could be interested in if I wanted to go that path.
Yeah. So just a second, we'll get to the courses right away. So here we have now the faculty. As you see, this covers a broad range of signal processing, communications, networking, with all these other related areas of power, arts, a bit more mathematical, some folks, a bit more applied, some other folks. So it's a very, very large group that we have here. I also want to point out that the professors in blue here are female faculty. So we have, in terms of gender, a reasonably good balance. I know electrical engineering is always challenging with gender balance, but we are doing quite well here at ASU, as you see here. Good. So then, okay, before we get to courses, one more thing. Where can all this get you? So here are different professions you can get into, different types of signal processing, engineering professions, ranging from just plain signal processing engineering, radar, image, multimedia, to communication networks. These are the potential companies that are working in this area. Intel is very large, hiring many of our our graduates. Qualcomm, of course, and all these others are very involved in hiring, providing internships and then hiring into permanent positions of our graduates. Now, to the courses. So going in this area, the Signals and Systems 1 is the first pathway course. Then you follow up with Signals and Systems 2, the EE 304, and then the EE 350, random signal theory, is then leading further into this topic area. The 350 is very important. This is a very broad class, has then a lot of applicability across the broad engineering, electrical and computer engineering two domains. So if you think about going into computer engineering, which is this interdisciplinary program, there will be a presentation in a few weeks. Computer engineering will require that you have 350 as a background, because computer engineering will require the graduate version of random signals and then the algorithms. So please, to get into this area, complete this entire sequence here, 203, 304, 350. And from there on, there are then various courses to deepen the signal processing. There's 407, 455 communication systems. These primarily is the so-called physical layer, signals that are being transmitted over communication systems. So you look at the frequency characteristics, timing characteristics. And 459 communication networks will then look at the higher layers of the internet protocol stack. So you start at a link layer, data link layer, all the way to network transport application layer. So it's a bit more towards computer science, almost more protocols oriented, covering the TCP/IP protocol stack, essentially, all the way to the application layer. 404, real-time TSP, is again signal processing, focused on real-time. And there's a whole bunch more courses that are listed out here at the graduate level that you may be interested in or may then take if you're going on into a master's or PhD program. Further classes, communications and coding. And then you have also these special interest courses that are fairly new. These cover emerging topics, also very, very interesting. Now, generally, to wrap this up and kind of summarize as you have seen through the courses, the field of signal processing communications is advancing quite rapidly. There are many new emerging technologies. And so it is a push to go with a hiring, go beyond the bachelor's, to go more towards master's and PhD. Traditionally, PhD has mostly been reserved for universities, teaching faculty positions, but there's more and more PhD hiring by commercial companies, just because these topics are getting so complex that PhD level of understanding and inquiry is needed to really make progress on these frontiers of engineering and science. So the big companies, Intel, Qualcomm, etc., are hiring many, if not most, of our PhDs currently. At ASU, they have very efficient ways to get to a master's. There's a 4+1. There's also a special presentation on that shortly. Also, if you are currently in the undergrad program and you are a US citizen, there's a very, very strong demand for signal processing communications engineers that can get security clearance later. as you can imagine, communications relates very closely to these very sensitive information systems. So there's an enormous demand. These labs and organizations and companies are really desperate for advanced studies and US citizens that have advanced studies in communication signal processing. So it's a very prosperous field to get into. At ASU, we have also a direct PhD that gets you the PhD really efficiently. And you can wrap up master's and PhD in 4 years. Some do it even faster. I've seen some students do it in 2.5, 3 years if you really push and get lucky with the research. I think I'm not redundant. Any questions, concerns?
There is one in the chat there. If you,
All right, let me pull this up here. It's always difficult. The most, it's very difficult. Many of these careers and many of these fields are very popular. It's really hard to identify the most important and most popular. Personally, from my perspective of networking, communication networking, there's a lot of push in the 5G, 6G area with low latency communication, weaving in industrial control with communications. There's enormous potential. It is also that, again, this theme of low latency is very important. Also from military perspective, there's efforts going on. There's all this buzz about hypersonic missiles and defenses and so on. As you can imagine, for quick reactivity, low latency is critical. And the underlying issue here is that the internet, as we know it, has been built on a best effort model. So latency has never been important. It's always been about throughput. And so low latency requires re-engineering everything, and that is a big effort. And so this theme of systems, protocols that support low latency is important all the way through. The radar, well, radar is a bit of a fringe topic here in itself. Radar oftentimes is integrated. So classical radar, is kind of a smaller area. However, the radar systems integrated in the larger systems, that is very important. Signal processing would be the way to go. Ideally, though, combined with maybe some background in antennas. So you have some physical understanding and also some electronics, microcircuits. The important thing maybe to point out here is this kind of these seminars focusing on a particular area. It may also be a little deceiving, which certainly need to specialize, but it's also very important to have the big picture because in the end it does come all together. So you to make innovations from the antennas. Through circuitry, through communications, through the protocols, everything is to incorporate. So as a student, you should specialize in an area, but you do need it from the broad perspective as well. So those depth and breadth are important. Yeah. Does that answer your question? Any other questions, concerns?
I don't know if you see that question there, Dr. Reisland, but asking more of a favorite example of signal processing that you've studied.
Again, very difficult. There's so much that's interesting. I think the multimedia processing is maybe the most interesting. From my perspective, again, it relates to communications, streaming. So video signal processing is very important. Most recently, I think the big push is into point clouds. So augmented reality, virtual reality, and getting these 3D immersive point cloud environments efficiently, ideally in real time, transmitted over the internet. That is the new challenge, and there's a big standardization effort going on in MPEG to develop protocols and compression algorithms for that. Signal processing, the communications in the AR, VR, XR space. Yeah.
And
So
maybe, Dr. Iceland, if you don't, a lot of students, and I don't quite understand it, but there's a significant crossover between this. It's not a new field, but the phrase data sciences gets used a lot, and it gets conflated with signal processing a lot. Do you see a difference there, or is it all overlap, or what do you think about?
There's some overlap, but also distinctions. I mean, so from a signal processing perspective, usually the focus is on processing these signals. And yes, there's an effort often to extract in these signals a deeper meaning through classical signal processing techniques, such as Fourier transforms, or all these variety of transforms that are out there, wavelets and so on, more advanced concepts. So that's the signal processing perspective. In addition, signal processing is also in a way merging or fusing or adopting data science concepts that the artificial intelligence, learning algorithms, deep learning, neural networks are finding their way into signal processing to enhance and complement classical techniques. So it's a cross-fertilization, if you will, between data sciences and signal processing. But signal processing does have its distinct roots, definitely. You're based more on the classical, they come from the perspective of classical transform-oriented signal processing.
Thanks. I think we have one additional question. And I will say it's from Yesenia. She's asking about, besides taking the courses and undergraduate research, are there other ways you can get hands-on experience about signal processing and communications? I mean, first, we always encourage students who are with us to consider work and internship experiences, but are there other things that come to mind, or activities they can do to learn more about this? I know personally I like to screw around with music, and if you download some of these apps, you can, do it depends on what level you're talking about, but there are some pretty sophisticated audio applications where you can manipulate, sound signals on iPads, and they're kind of fun. You can get pretty in depth on those. What other ideas come to mind?
I think the most important is probably the internship, yes. And again, to emphasize here, these internships in this area, signal processing, communications, is related computer engineering, are very important, often lead to also very well-paid positions. So there's an enormous demand. Again, especially if you are a US citizen and are okay with going into the security, defense-related areas. I know there's some ethical considerations as well that play into this. So it's a complicated topic, but if you're open to exploring these defense security-related areas, there are lots of internship opportunities that are out there that can lead to very, very interesting work. The other thing, of course, at ASU had the undergrad research initiative, the FURI. If you have a Fulton undergrad research topic on communications, there are several out there. Exploring those will be interesting, or going into a related topic in UC design. Yeah, there's the SPCom folks are quite active in UC design space as well. Yeah.
Yeah, you're right. I should have said capstone, but depending on your level, there might be some first-year students in the group today, and mainly my message is always go in there and play around with whatever you can get your hands on, and then formalize it through internships, capstone projects, classes, all that kind of stuff. But also be playing around a lot and having fun.
It's both important for personal passion, pursue it, but it's with a dual track, right? At the same time, you need at some point to acquire the theoretical background to comprehend what is going on under the hood. Yeah. And as engineers, we want to be develop what is under the hood, and so it requires a fairly comprehensive understanding of these complicated topics. Yeah.
And I think I have one final question for you from Sheldon, asking about if you have experience with these particular defense companies.
Yeah, well, here in our area, General Dynamics is very big. But the other thing to keep in mind, which I'm experiencing more and more, is that all the other garden variety chip makers and other companies are being drawn in more and more into this defense space. Yeah, so at Intel, for instance, there is a lot of subcontracts going on from Intel to defense organizations and back and forth. So even if you think, well, this is a just civilian electronics company, many of these do have military defense-oriented or security-related activities that are oftentimes not so openly, extensively publicized, but they are ongoing. And so it never hurts to ask and explore, and there's enormous demand.
If you see that last one from
Yeah,
Caleb.
very specific radio frequency satellite. I would be very active on Handshake, look around and be proactive in contacting these big companies. There's so many companies also, right? You Google around, you find various, aside from General Dynamics, there's so many others, big and small, and surprisingly large number of small companies in the area that you may have never heard of, that I've never heard of, because of the military has this requirement to have small businesses involved. And there are many actually small 5-6 people companies out here in Tempe, actually some are very close to ASU, that are doing very advanced stuff. So be on Handshake, be open, be available, have your public profiles open for everybody to view, and contact, Google around and contact those folks. There is a big demand.
Yeah, and then the only other thing to add to that is from our level, I'm not an engineer, of course, but we see students get position offers. And a funny anecdote from the last graduate career fair was one of the employers was in defense, and pretty much just asked anybody in the line if they've done any project that they have some sort of special clearance for, and they just ushered him to the front of the line and gave him a job on the spot. So sometimes when you do research with a faculty member and that research is related to a government contract in defense or something like that, there might be some clearance involved in that, and that clearance alone could be the kind of the golden ticket to really getting in that field. So that I've noticed that just from my level is not working in there, but these clearances are very important. So it's important to behave in a way that you can get that clearance and work with people who have it themselves.
Yeah, and maintain good relationship with the professors being known, because I, for instance, get oftentimes asked to support these clearance requests. There's actually a local office here in Phoenix that does these clearances, and they have to get on the phone with these folks and explain, how do you know the student? Is there any funny thing going on? So try to get personally introduced to your professors in your undergrad classes, so they can vouch for you to ease the process, because it is a painful process, and the more folks you can have, professors at the reputable places, the better and easier this process.
Yeah, Caleb, thanks. That was a really interesting question. So we see it too. Sometimes they'll call advising offices and ask us to vouch for students, and you know, honestly, sometimes we're not comfortable doing unless we truly know who they are, because it's it's a serious.
That's why it's very important to kind of have a personal rapport with a student, and especially if you then have worked as a grader or tutor or undergrad TA, or these opportunities are what I usually see as the best way to say, okay, I've worked with a student as a grader or undergrad TA. I'm really comfortable and confident to watch for the person. Yeah.
Well, thank you, Dr. Reislein. I think we've gotten through most of it. We're near the end here, but we really appreciate your time. It's great that faculty come to these and have live chats, and thanks to the students, particularly the online students. We love talking to you in real time. So thanks for taking the time out of your days to do this, everyone.